Okay, welcome back everybody. So in this lecture, what we're going to talk about is the idea of continuity, and we're only going to talk about it informally. Next lecture, we will introduce the concept of a limit and then give a formal and rigorous definition for continuity. But at least for today, I just want to talk a little bit about continuity and then one of the main applications of the idea of continuity, which is the intermediate value theorem. Okay, so I talked a little bit in the first video about what continuity kind of is. So maybe let's switch to different colors. So definition, at least an informal definition of continuity. So a function f of x is continuous on the interval maybe we'll just call it a to b. So a and b here are real numbers. So f of x is continuous on this interval if the graph of f of x is connected and has no sort of jumps in it. Really, if it has no discontinuities. So a way to think about this is a function is continuous if its graph can be drawn without picking up your pen. So maybe we'll add that as a second definition. Maybe this is an informal definition. The first one is also informal. A function is continuous if its graph can be drawn without picking up your pen. Or pencil, or Sharpie, or highlighter, or whatever you're choosing to write with. Maybe a quill and ink. Who knows? Okay, so examples of continuous functions, or at least examples of graphs of continuous functions. So maybe we'll just draw a few of these. So an example of a continuous function would be something like this. Or maybe, you know, I start down here and then I have a little cusp, like a sharp cusp, but that's not a problem. That's still continuous. So these would both be continuous. And then something which is not continuous would be something that does, you know, something like this, where it just jumps down to another value at a particular point. Okay? So this would not be continuous. So there are a few different types of discontinuities that can happen. So maybe a third definition would be a function f is continuous if it has no discontinuities. So let's talk about the kinds of discontinuities that we can have. We already see one right here, but there are a couple of others that I want us to be familiar with and be able to classify. So kinds of discontinuities. And there are really three main kinds. So let's go ahead and just draw a picture of each of them. And I think that they're not too challenging to understand. It's just a matter of giving them a name and defining them properly. So the first kind is, like we've already seen, it is a jump discontinuity. So the graph, you know, is continuous, and then it jumps to another point. So it kind of jumps from this point down to this one. The next kind is an infinite discontinuity. So maybe if you recall the graph of like, 1 over x, then its graph looks something like this, where the infinite discontinuity is happening when x is equal to 0. As x approaches 0 from one side or the other, it's going to shoot off towards positive or negative infinity. As x gets closer to 0, you're dividing by a smaller and smaller number, which is the same thing as multiplying by a very large number. So it's going to have an infinite discontinuity at x equals 0. The third kind is a removable discontinuity. Removable. And we call them these removable discontinuities. So the removable discontinuity might look something like this, where there's just a single point where the graph is discontinuous. These are called removable because we could just simply modify the function at this singular point, or maybe at a finite set of points, and then just remedy all of the discontinuities of this function. So there's no real problem here. It's just at this one point the function is misbehaving in a sense. Okay, so these are the three kinds of discontinuities, and if a graph has any of these sorts of things, or if the graph of a function exhibits any of these things, we say that the function is discontinuous. And if it doesn't have any of these, then we say that the function is continuous. Okay, so those are the different kinds of discontinuities. The next thing I want to talk about is just a simple concept of continuity. We can divide this into continuity from the left and the right. So one-sided continuity is the thing I want to talk about next. Okay, so really there's, again, just a pair of pictures that I want to draw that sort of clarify what I mean by this. And again, this is all informal for the moment. Tomorrow, or maybe not tomorrow when you're watching this, but whenever you watch the next lecture, in the next lecture we're going to rigorously define these things. So let's call this one continuous from the left and continuous from the right. And a graph that is continuous from the left is going to look something like this. So I have my function, I'm coming in from the left, so I'm coming from the left side here, and I'm going to actually attain the value that I'm approaching from the left, and then I jump down to another value on the right side. So as I come in from the right, I don't actually hit the value that I look like I'm approaching. I jump up to this one. So here I would be continuous from the left and discontinuous from the right. And then same thing, the analogous thing is true over here, but now I would just switch which thing I fill in. So I have here I'm continuous from the left, discontinuous from the right. Here I'm continuous from the right, discontinuous from the left. And again, it's because I'm attaining, as I approach from the right side, from positive infinity, I attain the value that it sort of looks like I'm approaching. Same thing here, as I approach from the left, I attain the value that I look like I'm approaching. But if I approach from the right here, I don't attain the value I expect. And here, if I approach from the left, I don't attain the value that I expect. Okay? And then we might add yet another definition for continuity. A function is continuous, maybe at a point C, if it is continuous from the left and from the right. At C. Okay, so you hit the expected value of your graph no matter which side you approach from. Okay, so that's sort of the intuitive idea of continuity. Again, the thing to think about with continuity and the idea that I want you all to have in mind is that it's really just about, is the graph sort of connected or not? Do you have these jumps? Do you have these sort of infinite discontinuities? Do you have these single points that you could remove? And if you don't, then you're going to be continuous. Okay, the next big idea that I want to talk about is the intermediate value theorem. And the intermediate value theorem deals with zeros of functions, and namely the location of zeros of functions. So what does the intermediate value theorem say? Maybe let's write out the statement of the theorem, and then we can talk about what it's actually saying. So I'm just going to abbreviate this from now on, IVT, for intermediate value theorem. And I'm actually going to put a red star next to this because this is important to know. So if a function is continuous on the interval a to b, so it doesn't exhibit any of these sort of properties that we talked about before, and if the function changes sign over the interval, or over this interval, i.e. f of x, or I should say meh. So f of a is negative, and then f of b is positive, or the reverse is true. F of b is negative, and f of a is positive. Then f of x has a 0, and a 0 of the function is a point c with f of c equal to 0 in the interval a to b. And really, I should make this an open interval. This is not the fully general version of the intermediate value theorem, but for our purposes, this is all that we're going to use it. This is the form that we're going to use it in. Okay, so if a function is continuous, and I will underline that continuous is a very important part of this. This entire theorem is not true at all if we are not continuous. And if we change sign over this interval, again, these are the two really important hypotheses, then we know that f of x has a 0 in this interval. And you might ask, what is the benefit of knowing that f of x has a 0 in a certain interval? Well, you can think about perhaps many examples where you might want to know that f of x has a 0 in this interval. So if f of x represents maybe a profit function, you would really want to know when your profit is equal to 0 and when your profit switches from positive to negative. This is a very important piece of information if you're doing economics. So what does this theorem say? Well, maybe let's just illustrate this with a picture. So if I have a function, and maybe here's my a, here's my b, and then here's my function on one side, and I'm continuous and I switch sign over the interval, then I have to have a 0. And if I'm continuous, so I can't just, pass through, I can't do something like this, where I do some witchcraft with discontinuity, and I switch to being negative right here. This is not what we want. So if I'm continuous and I switch sign over an interval, then I have to pass through 0. So if I'm negative on one side, positive on the other, and I'm continuous, you are necessarily forced to pass through the value 0. And that's what the intermediate value theorem says. We're not going to prove this, and it's actually somewhat challenging to prove this, although it doesn't seem like it would be. At least in the general case, this is challenging. But yeah, this is the intermediate value theorem. As a concrete example of kind of reasoning with the intermediate value theorem, let's maybe do something like this. So using the intermediate value theorem, show that f of x, which is equal to, I don't know, let's do something really simple, x minus 2 has a 0 in the interval, let's say maybe 0 to 3. Okay, so f of x, so to use the intermediate value theorem, there are two things we need to check. So one, f of x is a line, so f of x is continuous. So that's the main thing the first thing we have to check is that f of x is continuous. Lines are clearly continuous, so that's just one way of seeing this, but in any case, all you need to sort of justify is that f of x is continuous. That's what we need to, that's one of the assumptions that we need in order to apply the intermediate value theorem. The second thing is that we need to know that f of x changes sign over this interval. So how do we show that? Well, f of 0 is what? It's negative 2. And f of 3 is equal to positive 1. You just plug those numbers in, and these are what you get out. So f of 0 is negative, and that's less than f of 1, or f of 3, I'm sorry. And f of x changes sign in 0 to 3. Well, f of x is continuous, f of x changes sign in 0 to 3, therefore does therefore have an e in it? I don't actually know. I never can remember. By the intermediate value theorem, f of x has a 0 in 0 to 3. Okay, and that's all we have to say. We've checked the two hypotheses, namely continuity and changing sign over the interval, and therefore the intermediate value theorem applies, and we just assert that by the intermediate value theorem, the conclusion, namely that f of x has a 0 in 0 to 3. Okay, so that's everything I wanted to cover in this lecture. The next thing that we're going to talk about is we're going to introduce the idea of a limit. It's one of the most fundamental concepts in calculus, and really the thing that makes everything go around in calculus. So we'll use that to give a rigorous definition of continuity, and then from there we'll move on to properties of limits, and then ultimately get to the first major concept, which is that of a derivative. All right, see you guys in the next lecture.